Chapter 13 of the Story of Alchemy. This LibriVox recording is in the public domain. Recording by Peter Yearsley. The Story of Alchemy and the Beginnings of Chemistry by M. Pattison Muir. Chapter 13. The chemical elements contrasted with the alchemical principles. It was known to many observers in the later years of the 17th century that the product of the calcination of a metal weighs more than the metal. But it was still possible at that time to assert that this fact is of no importance to one who is seeking to give an accurate description of the process of calcination. Weight, which measures mass or quantity of substance, was thought of in these days as a property like colour, taste, or smell, a property which was sometimes decreased and sometimes increased by adding one substance to another. Students of natural occurrences were, however, feeling their way towards the recognition of some property of substances which did not change in the haphazard way wherein most properties seemed to alter. Lavoisier reached this property at one bound. By his experimental investigations he taught that, however greatly the properties of one substance may be masked or altered by adding another substance to it, yet the property we call mass, and measure by weight, is not affected by these changes, for Lavoisier showed that the mass of the product of the union of two substances is always exactly the sum of the masses of these two substances, and the sum of the masses of the substances whereinto one substance is divided is always exactly equal to that mass of the substance which is divided. For the undefined, ever-changing, protean essence or soul of a thing, which the alchemists thought of as hidden by wrappings of properties, the exact investigations of Lavoisier, and those of others who worked on the same lines as he, substituted this definite, fixed, unmodifiable property of mass. Lavoisier, and those who followed in his footsteps, also did away with the alchemical notion of the existence of an essential substratum, independent of changes in those properties of a substance which can be observed by the senses. For the experimental researches of these men obliged naturalists to recognise that a change in the properties of a definite homogeneous substance, such as pure water, pure chalk, or pure sulphur, is accompanied, or, as we generally say, is caused, by the formation of a new substance or substances. And this formation, this apparent creation of new material, is effected either by the addition of something to the original substance, or by the separation of it into portions which are unlike it, and unlike one another. If the change is a combination or coalescence of two things into one, then the mass, and hence the weight, of the product is equal to the sum of those masses, and hence those weights, of the things which have united to form it. If the change is a separation of one distinct substance into several substances, then the sum of the masses, and hence the weights, of the products is equal to that mass, and hence that weight, of the substance which has been separated. Consider the word water, and the substance represented by this word. In Chapter 4 I gave illustrations of the different meanings which have been given to this word. It is sometimes used to represent a material substance, sometimes a quality more or less characteristic of that substance, and sometimes a process to which that substance, and many others like it, may be subjected. But when the word water is used with a definite and exact meaning, it is a succinct expression for a certain group or collocation of measurable properties, which are always found together, and is therefore thought of as a distinct substance. This substance can be separated into two other substances very unlike it, and can be formed by causing these to unite. 100 parts by weight of pure water are always formed by the union of 11.11 parts of hydrogen and 88.89 parts of oxygen, and can be separated into these quantities of those substances. When water is formed by the union of hydrogen and oxygen in the ratio of 11.11 parts by weight of the former to 88.89 of the latter, the properties of the two substances which coalesce to form it disappear, except their masses. It is customary to say that water contains hydrogen and oxygen, but this expression is scarcely an accurate description of the facts. What we call substances are known to us only by their properties, that is, the ways wherein they act on our senses. hydrogen has certain definite properties, oxygen has other definite properties, and the properties of water are perfectly distinct from those of either of the substances which it is said to contain. It is therefore somewhat misleading to say that water contains substances, the properties whereof, except their masses, disappeared at the moment when they united and water was produced. Nevertheless, we are forced to think of water as, in a sense, containing hydrogen and oxygen. For one of the properties of hydrogen is its power to coalesce or combine with oxygen to form water, and one of the properties of oxygen is its ability to unite with hydrogen to form water, and these properties of those substances cannot be recognised or even suspected unless certain definite quantities of the two substances are brought together under certain definite conditions. The properties which characterise hydrogen, and those which characterise oxygen, when these things are separated from all other substances, can be determined and measured in terms of the similar properties of some other substance, taken as a standard. These two distinct substances disappear when they are brought into contact, under the proper conditions, and something, water, is obtained whose properties are very unlike those of hydrogen or oxygen. This new thing can be caused to disappear, and hydrogen and oxygen are again produced. This cycle of changes can be repeated as often as we please. The quantities of hydrogen and oxygen which are obtained when we choose to stop the process are exactly the same as the quantities of those substances which disappeared in the first operation, whereby water was produced. Hence water is an intimate union of hydrogen and oxygen, and in this sense water may be said to contain hydrogen and oxygen. The alchemist would have said the properties of hydrogen and oxygen are destroyed when these things unite to form water, but the essence or substratum of each remains. The chemist says you cannot discover all the properties of hydrogen and oxygen by examining these substances apart from one another, for one of the most important properties of either is manifested only when the two mutually react. The formation of water is not the destruction of the properties of hydrogen and oxygen, and the revelation of their essential substrata. It is rather the manifestation of a property of each, which cannot be discovered except by causing the union of both. There was, then, a certain degree of accuracy in the alchemical description of the processes we now call chemical changes, as being the removal of the outer properties of the things which react, and the manifestation of their essential substance. But there is a vast difference between this description and the chemical presentment of these processes as reactions between definite and measurable quantities of elements or compounds, or both, resulting in the redistribution of the elements, or the separation of the compounds into their elements, and the formation of new compounds by the recombination of these elements. Let us contrast the two descriptions somewhat more fully. The alchemist wished to effect the transmutation of one substance into another. He despaired of the possibility of separating the elements whereof the substance might be formed, but he thought he could manipulate what he called the virtues of the elements by a judicious use of some or all of the three principles, which he named sulphur, salt, and mercury. He could not state in definite language what he meant by these principles. They were states, conditions, or qualities of classes of substances, which could not be defined. The directions the alchemist was able to give to those who sought to effect the changes of one thing into another were these: firstly, to remove those properties which characterized the thing to be changed, and leave only the properties which it shared with other things like it. Secondly, to destroy the properties which the thing to be changed possessed in common with certain other things. Thirdly, to commingle the essence of the thing with the essence of something else, in due proportion, and under proper conditions. And finally, to hope for the best, keep a clear head, and maintain a sense of virtue. If he who was about to attempt the transmutation inquired how he was to destroy the specific properties, and the class properties, of the thing he proposed to change, and by what methods he was to obtain its essence, and cause that essence to produce the new thing, he would be told to travel along the road which was followed by the great architect of the universe in the creation of the world, and if he demanded more detailed directions, he would be informed that the substance wherewith his experiment began must first be mortified, then dissolved, then conjoined, then putrefied, then congealed, then cibated, then sublimed and fermented, and finally exalted. He would, moreover, be warned that in all these operations he must use not things which he could touch, handle, and weigh, but the virtues, the lives, the souls of such things. When the student of chemistry desires to effect the transformation of one definite substance into another, he is told to determine by quantitative experiments what are the elements and what the quantities of these elements which compose the compound which he proposes to change, and the compound into which he proposes to change it, and he is given working definitions of the words element and compound. If the compound he desires to produce is found to be composed of elements different from those which form the compound wherewith his operation begin, he is directed to bring about a reaction, or a series of reactions, between the compound which is to be changed and some other co-location of elements, the composition of which is known to be such that it can supply the new elements which are needed for the production of the new compound. Since Lavoisier realised for himself and those who were to come after him the meaning of the terms element and compound, we may say that chemists have been able to form a mental picture of the change from one definite substance to another which is clear, suggestive, and consistent, because it is an approximately accurate description of the facts discovered by careful and penetrative investigations. This presentment of the change has been substituted for the alchemical conception, which was an attempt to express what introspection and reasoning on the results of superficial investigations, guided by specious analogies, suggested ought to be the facts. Lavoisier was the man who made possible the more accurate and more far-reaching description of the changes which result in the production of substances very unlike those which are changed, and he did this by experimentally analysing the conceptions of the element and the compound, giving definite and workable meanings to these conceptions, and establishing on an experimental foundation the generalisation that the sum of the quantities of the substances which take part in any change is itself unchanged. A chemical element was thought of by Lavoisier the actual term whereat analysis has arrived, a definite substance which we cannot subdivide with our present knowledge, but not necessarily a substance which will never be divided. A compound was thought of by him as a definite substance which is always produced by the union of the same quantities of the same elements, and can be separated into the same quantities of the same elements. These conceptions were amplified and made more full of meaning by the work of many who came after Lavoisier, notably by John Dalton, who was born in 1766 and died in 1844. In Chapter 1 I gave a sketch of the atomic theory of the Greek thinkers. The founder of that theory, who flourished about 500 BC, said that every substance is a co-location of a vast number of minute particles, which are unchangeable, indestructible, and impenetrable, and are therefore properly called atoms; that the differences which are observed between the qualities of things are due to differences in the numbers, sizes, shapes, positions, and movements of atoms, and that the process which occurs when one substance is apparently destroyed and another is produced in its place is nothing more than a rearrangement of atoms. The supposition that changes in the properties of substances are connected with changes in the numbers, movements, and arrangements of different kinds of minute particles was used in a general way by many naturalists of the 17th and 18th centuries, but Dalton was the first to show that the data obtained by the analyses of compounds make it possible to determine the relative weights of the atoms of the elements. Dalton used the word atom to denote the smallest particle of an element or a compound which exhibits the properties characteristic of that element or compound. He supposed that the atoms of an element are never divided in any of the reactions of that element, but the atoms of a compound are often separated into the atoms of the elements whereof the compound is composed. Apparently without knowing that the supposition had been made more than 2000 years before his time, Dalton was led by his study of the composition and properties of the atmosphere to assume that the atoms of different substances, whether elements or compounds, are of different sizes and have different weights. He assumed that when two elements unite to form only one compound, the atom of that compound has the simplest possible composition, is formed by the union of a single atom of each element. Dalton knew only one compound of hydrogen and nitrogen, namely ammonia. Analyses of this compound show that it is composed of 1 part by weight of hydrogen and 4.66 parts by weight of nitrogen. Dalton said one atom of hydrogen combines with one atom of nitrogen to form an atom of ammonia. Hence, an atom of nitrogen is 4.66 times heavier than an atom of hydrogen. In other words, if the atomic weight of hydrogen is taken as unity, the atomic weight of nitrogen is expressed by the number 4.66. Dalton referred the atomic weights of the elements to the atomic weight of hydrogen as unity, because hydrogen is lighter than any other substance. Hence the numbers which tell how much heavier the atoms of the elements are than an atom of hydrogen are always greater than 1, are always positive numbers. When two elements unite in different proportions by weight to form more than one compound, Dalton supposed that, in most cases at any rate, one of the compounds is formed by the union of a single atom of each element. The next compound is formed by the union of one atom of the element which is present in smaller quantity with 2, 3, or more atoms of the other element. And the next compound is formed by the union of one atom of the first element with a larger number, always necessarily a whole number, of atoms of the other element than is contained in the second compound. And the next compound is formed by the union of one atom of the first element with a larger number, always necessarily a whole number, of atoms of the other element than is contained in the second compound, and so on. From this assumption, and the Daltonian conception of the atom, it follows that the quantities by weight of one element which are found to unite with one and the same weight of another element must always be expressible as whole multiples of one number. For if two elements, A and B, form a compound, that compound is formed by supposition of one atom of A and one atom of B. If more of B is added, at least one atom of B must be added. However much of B is added, the quantity must be a whole number of atoms, and as every atom of B is the same in all respects as every other atom of B, the weights of B added to a constant weight of A must be whole multiples of the atomic weight of B. The facts which were available in Dalton's time confirmed this deduction from the atomic theory, within the limits of experimental errors, and the facts which have been established since Dalton's time are completely in keeping with the deduction. Take, for instance, 3 compounds of the elements nitrogen and oxygen. That one of the 3 which contains least oxygen is composed of 63.64% of nitrogen and 36.36% of oxygen. If the atomic weight of nitrogen is taken to be 4.66, which is the weight of nitrogen that combines with 1 part by weight of hydrogen, then the weight of oxygen combined with 4.66 of nitrogen is 2.66. Note, the ratio of 63.64 to 36.36 is equal to 4.66 to 2.66. End note. The weights of oxygen which combine with 4.66 parts by weight of nitrogen to form the second and third compounds respectively must be whole multiples of 2.66. These weights are 5.32 and 10.64. Now, 5.32 equals 2.66 times 2, and 10.64 equals 2.66 times 4. Hence the quantities by weight of oxygen which combine with one and the same weight of nitrogen are such that 2 of these quantities are whole multiples of the third quantity. Dalton's application of the Greek atomic theory to the facts established by the analyses of compounds enabled him to attach to each element a number which he called the atomic weight of the element, and to summarize all the facts concerning the composition of compounds in the statement that the elements combine in the ratios of their atomic weights, or in the ratios of whole multiples of their atomic weights. All the investigations which have been made into the compositions of compounds since Dalton's time have confirmed the generalization which followed from Dalton's application of the atomic theory. Even if the theory of atoms were abandoned, the generalization would remain as an accurate and exact statement of facts which hold good in every chemical change, that a number can be attached to each element, and the weights of the elements which combine are in the ratios of these numbers, or whole multiples of these numbers. Since chemists realized the meaning of Dalton's book, published in 1808, and entitled A New System of Chemical Philosophy, elements have been regarded as distinct and definite substances, which have not been divided into parts different from themselves, and unite with each other in definite quantities by weight, which can be accurately expressed as whole multiples of certain fixed quantities. And compounds have been regarded as distinct and definite substances, which are formed by the union of, and can be separated into, quantities of various elements, which are expressible by certain fixed numbers or whole multiples thereof. These descriptions of elements and compounds are expressions of actual facts. They enable chemists to state the compositions of all the compounds which are, or can be, formed by the union of any elements. For example, let A, B, C, and D represent 4 elements, and also certain definite weights of these elements. Then the compositions of all the compounds which can be formed by the union of these elements are expressed by the scheme AN, BM, CP, DQ, where M, N, P, and Q are whole numbers. These descriptions of elements and compounds also enable chemists to form a clear picture to themselves of any chemical change. They think of a chemical change as being 1. A union of those weights of 2 or more elements which are expressed by the numbers attached to these elements, or by whole multiples of these numbers, or 2. A union of such weights of 2 or more compounds as can be expressed by certain numbers, or by whole multiples of these numbers, or 3. A reaction between elements and compounds, or between compounds and compounds, resulting in the redistribution of the elements concerned, in such a way that the complete change of composition can be expressed by using the numbers or whole multiples of the numbers attached to the elements. How different is this conception of a change wherein substances are formed entirely unlike those things which react to form them, from the alchemical presentment of such a process. The alchemist spoke of stripping off the outer properties of the thing to be changed, and by operating spiritually on the soul which was thus laid bare, inducing the essential virtue of the substance to exhibit its powers of transmutation. But he was unable to give definite meanings to the expressions which he used. He was unable to think clearly about the transformations which he tried to accomplish. The chemist discards the machinery of virtues, souls, and powers. It is true that he substitutes a machinery of minute particles, but this machinery is merely a means of thinking clearly and consistently about the changes which he studies. The alchemist thought vaguely of substance as something underlying and independent of properties. The chemist uses the expression this or that substance as a convenient way of presenting and reasoning about certain groups of properties. It seems to me that if we think of matter as something more than properties recognized by the senses, we are going back on the road which leads to the confusion of the alchemical times. The alchemists expressed their conceptions in what seems to us a crude, inconsistent, and very undescriptive language. Chemists use a language which is certainly symbolical, but also intelligible, and on the whole fairly descriptive of the facts. A name is given to each elementary substance, that is, each substance which has not been decomposed. The name generally expresses some characteristic property of the substance, or tells something about its origin or the place of its discovery. The names of compounds are formed by putting together the names of the elements which combine to produce them, and the relative quantities of these elements are indicated either by the use of Latin or Greek prefixes, or by variations in the terminal syllables of the names of the elements. Chapter XIV.